So yeah, that's the idea here. Now the thing is, we have to try to make it a bit efficient, if or at least efficient enough to complete on time. Um, so how do we do that? How do we find the cost um, for converging onto node I and then going the rest of the way? Well, the cost of that is going to be equal to the b times the uh, number of paths that we have to go to from node 1 to node I. So node 1 is where Bessie is, right? And then plus e times get num paths from node 2 to node I, right? Node 2 is where Elsie is, plus the energy expenditure of going the rest of the way from node I to the destination node, right? So it'll be P times get num paths from node I to node N. So N is our destination node in this case. So with this formula here, so get num paths, like I said, with breadth first search, we can get the number of paths in between, the minimum number of paths between two nodes. However, if we do it this way, this could not run in time. Let's see, how many nodes are there? So in the problem, we have n equal to, I forgot, what is it? N is at most 40,000. Yeah, so if we loop through each node, and for each node we do an operation, a breadth first search here that takes that could also visit every single node. So that's another n operation. So it's n times n, and that's too slow. What we can do is modify BFS slightly so that we call it once and get the distance from a start node to every other node in the graph. Right. So if you look at my screen share, the diagram that I drew yesterday, where we have, no, that's not it. Where we have a graph, right, and we're trying to visit all the possible nodes that's traversable from the start node, right? So if I use a different color for the start node. So if this is my start node, the idea is with breadth first search, I can visit all the nodes that's reachable from that node, right? And with that also means that it only takes one breadth first search for us to figure out the distance from my start node to every other node that's reachable in the graph. So here's what I did in my solution. I implemented breadth first search, where it takes in the graph and it takes in the start node, and it returns an int array. So that int array represents the return array. The ith index represents the distance from the start node to node I, and we can do that. We can figure out the distance from that start node to every other node just by using one BFS. So with that, then that means we only need to do BFS a total of 3 times. Once from the start node of node 1, right, where Bessie is. Second time from the starting node of Elsie. And the last time, if we flip these indices, right, right, that doesn't change the equation. The last time what we can do is we actually go from the destination node and work our way backwards to every other node that could possibly be the node at which the two cows converge. So yeah, that's my solution. Any questions on this?
So,
Yeah.
why did you use an array list for the nodes?
Oh yeah. So I forgot to talk about that so the way I represent the graph is I use an array of array lists instead of. So yesterday we talked about how you can represent a graph by using like a Boolean 2D array, right? Like this, right? So I say so graph of ij denotes whether there is a path from node I to node j. So that works if there aren't that many nodes in the graph. Here, there are 40,000 nodes. So to represent that using this 2D array, yeah, sorry, I forgot to talk about this. To represent that using a 2D array, the 2D array is going to have to store 40,000 square number of booleans, and that's quite a bit. It's like 100 million, right? 160 million. Um, so yeah, actually, what's another way to represent a graph? So basically, what you really want is a mapping of for a given node I, who are its neighbors. Um, so if there aren't that many nodes, a 2D array is fine, but for this, like here's like several ways of represent it. You can have a map that maps a node to a list of nodes that it can get to. Or you can also have it be like that instead, where um, so here with the map representation, the key is node I, and the value is list of nodes reachable from node I. Right. Uh, or you can use a list here um, where array of I denotes a list of nodes reachable from node I. Either way works. Yep. Okay, so what I wanted to do today and tomorrow, like I said yesterday, it's mostly review. So I want to just go ahead and pull up a question and ask you guys how would we go about solving it together. So the first one is called Cownomics. All right, so here's the link. Go ahead and go ahead and read that. I don't know why there's only two of us today, but All right, are we good? Okay. So n. First of all, what's n? N is the number of spotted cows and the number of plain cows. Um, and n is at most 500. So if n is at most 500, that's actually a total of 1,000 cows, right? Um, okay, which is fine. And there's also m, which is the DNA sequence length of every single cow, um, from 3 to 50. Okay, so that's not very long. Now it says we have to find all possible triplets of positions where it contains columns of DNA that, when you look at them together, it would uh, the way it says it would explain, but it would totally determine whether the cow is spotty or plain. So, what is the necessary condition for that to happen? Uh, that would be for uh, indices I, J, K um, to to uh, explain spottiness. Uh, the the DNA the DNAs at those positions for spotted cows must be different from uh, the plain cows, right? All right, so at this point, it doesn't look like there's really any trick to optimize our code, right? It really sounds like we have to do a triple loop. Uh, okay. Now the thing is, there are so each of these loops, right? They run at most 500 iterations. Actually, let me use the Java comments here. So 500 here, 500 here, 500 here. So that's 500 cube. That's not too bad. Uh, but then we have to loop through each cow here, right? So we have to loop through each spotted cow and generate the DNAs and see like whether the plain cows, whether any of them matches uh, the the same DNA strings for the spotted cows. Um, so the naive way of doing this is we can say for each spotted cow S, and for each spotted cow C, sorry, it's for each plain cow C, check whether S and C have same DNA at positions I, J, K.
Well,
Note that this is at 500. Yeah, go
what does what does the K do here?
ahead. The IGK, so it's triplet of positions, right? Triplet of indices.
Yeah.
Right? So IGK are just indices.
But why three indices? Wouldn't you
Because
just need one for the start and one for the end?
no, those three positions can be anywhere. It doesn't have to be contiguous. So in the example, right, it says, looking carefully at this table, he surmises that positions 2 and 4 are sufficient to explain spottiness. That is like, so if he looks at only column 2 and column 4, he would know for sure whether the cow is spotty or plain. But the question's asking counts the number of triplets, 3 distinct positions that explain spottiness. So we just need a triple loop. All right. Now here, what I have is a bit unwieldy. It's 500 to the power of 5, and that is too slow. Okay. So we want to reduce the that number. Oh, actually, no, hold on. It's from 0 to m. Yeah, my mistake. That looks too intractable. So m is actually the length of the string, so it's just 50. So 50, 50, 50 here. So 50 cubed times 500 squared. All right, so that's equal to still a huge number, 31 billion. That's too slow. Any ideas on how to reduce this complexity? I'll give you a hint. Look at the innermost 2 loops. There's something inefficient about doing like a pairwise comparison for each spotted cow and for each plain cow, whether they have the same DNA. Can we make this a bit more efficient? Here's hints. Think of data structures that could decrease this runtime. Any ideas? So locally, the part that I'm highlighting, that runs in n square. I'll give you hints. We can reduce this to big O of n instead of n square by using an appropriate data structure. How about a hash set?
So we would like store each of the spotted cows like combinations in a hash set. Then for
Yeah,
each
yeah.
plain cow we check.
Right, exactly. So the idea is we can generate all the possible strings for the spotted cows, put in a hash set. So that requires us to loop n times, right, through those spotted cows, and that's fine. But the nice thing about constructing the hash set is now we can loop through the plain cows, right, and to determine whether it has the same DNA as any of the spotted cows, we just need to look into the hash set, right? So, and the hash is really efficient, right? It's big O of 1. So we can avoid this double loop if we use a hash set. Um, so we can have a hash set set and have that contains the DNA strings of all spotted cows at position ijk. So if we construct that, so that takes n iterations. But then afterwards, we can just say check if, sorry, for each plain cow, C, check whether its DNA string is contained in set. Right, so we're reducing those 2 innermost loops into two innermost nested loops into two separate loops. So this initializing this does require one loop, and then this one does also require its own loop, but they're separate, right? They're not nested together. And with that, our algorithm should be able to run in time. All right, questions on this? Okay, so let's move on to a different problem. This one's called cow dance. All right, here it is. So you can go and read that.
This kind of looks like a binary search problem.
Hmm. Good insight. Are we ready? Okay.
Oh, there's only 2 people here today.
Yeah. I don't know why. Uh, anyways, yeah. So you guys can like talk amongst yourselves. It's a really small group today. And yeah, I actually want to not do as much lecturing today. I would just be going over. I would just be showing you different problems and asking you guys how you would go about it. Uh, okay, so we have a dance stage, and we're trying to determine the size of the dance stage so that all the cows, if they're to be running in the sequence that they are specified, they're the end time of the show would be less than t. So Venkat, you mentioned binary search. Can you
Mm-hmm.
explain how that can be used here?
So, like, if a certain value of k works, then all values above it will take less time, so we can just count those out
Mm-hmm.
because we're looking for the minimum value of k. And if like a value doesn't work, then that means all the values below it won't work, so we can have the search space that way as well.
Right. Yeah. Yeah. So exactly. So we can find k being the sorry, we can find the k with the smallest value. Uh, wait, hold on. Let me get the terminations right. Uh, Determine the smallest possible value of k such that uh, the show runs on time, right? With the largest possible value of, specifying the largest possible value of t. So t max specifies it's the largest possible value of t. Right, so there's like a deadline of uh, how late the show can go. So if the dance stage is bigger, then the show would be strictly faster. If the would be strictly faster or at least as fast, and vice versa, right? So if you decrease the dance stage, it can't go any faster. It can only go slower. Uh, so yeah, because of that, we can use binary search to determine the appropriate value of k. So that's the first part of the problem, binary search, there's still the second part. Given a value of k, how do we determine its n time? The show's n time. So we got what is it? N cows, right? We got oops, wrong problem. We got n cows, and they each have to run. They each have to appear in that order, right? And um, um, so when one cow frees up, the next cow can go in, but we are not able to mess around with the ordering. So how do we know like what is the end time of the show?
Wait, if the second cow finishes dancing before the first cow, can the second cow leave, or
Yeah, the second
does
guy
the
can
second cow have to
leave,
stay and
and
fit?
then whoever's next up can fill his spot.
But how do we
Okay.
like order the cows into
Hmm.
spots such that they take the least amount of time?
Yeah, not obvious. I'll give you hints. Um, priority queue. You guys remember
But
priority queues?
would we go from biggest to smallest or smallest to biggest?
Mm, biggest, smallest to biggest. What quantity are you specifying here?
The amount of time the cow dances for.
Um, well, we can sort that, but it wouldn't help. Remember, the cows have to appear in the order that they're given. So
Oh,
we
really?
can't really, yeah. So we can't really change the ordering. Yeah.
Wait, what's a priority
Oh,
queue
okay, never mind
again?
then.
All right. Yeah. So let's go over that. So a priority queue is similar to a tree set, but it allows duplicates. It it self sorts elements within the data structure, and duplicates are allowed. Okay. So the idea is it's got three different operations. You can add an element to the priority queue. You can do size, of course, uh, and you can do something called poll, which removes the smallest element in the priority queue. Yep. So what we can do here is we can loop through the cows in the order that they are given to us. So cows of I denotes the duration of cow I. All right. Uh, so we really don't have a say as to like if we can shuffle the order of the cow. The answer is no. We have to traverse them in order. Uh, but in the we can create a priority queue that simulates the cows that are currently on the dance stage, right? So we do need to keep track of cows that are on this dance stage, but we also need a way to say, okay, which cow is going to go next, right? Which one is going to be off the stage next? And with a priority queue, that it's a good data structure for this because we can add things in. The elements can be duplicates, and we can poll. We can do poll, right, which removes the smallest element in the priority queue. So we can have a priority queue of integer, and they do store cows. Well, they do kind of simulate storing the cows, but we're not going to be prioritizing the cows by the duration.
Well, why don't we just put them in the queue in the order they give them to us?
We should be doing that. But what number do we actually put in the queue? Because when we poll, right, we're polling the smallest number from the
But
queue.
can't we just add all of the different cows' values in order and then like pop each one
The
or
duration,
whatever it's called?
the durations.
Yeah, and then
Uh,
take like the next one. I forget what that's called
right,
for a
right.
queue.
So we can calculate something with the duration. We can calculate their n times. So we can have this priority queue store the n times of each cow that's currently on stage. Right, so let's go through the example. Okay, so we have the sample input, right? So with 5 cows here, and their durations are 4, 7, 8, 6, 2. And let's say k is 2 to begin with. So that would mean like, okay, the first cow, which has a duration of 4, would be up, but at the same time, the next cow, which has a duration of 7, can also be up, right? Now, who's going to get finished first? Well, obviously this cow, right? And then the next cow can come in. So that cow has a duration of 8. Okay. And now in that case, like which one is going to finish first? This cow or that cow? Whoops. This cow or that cow? Well, this cow is going to finish first, and when he finishes, we can put the next cow, which has a duration of 6, onto this stage, right? And then you compare these two and say, okay, um, this one's going to finish first, right? So we can put the last cow, which has a duration of 4, into the stage. Okay, so this is going to be your total time. So, like, I guess a more natural way of thinking about this is you can almost use an array of length k, right? There's essentially like k slots in the dance stage, right? And like whoever comes in, right? Let's say all k slots are occupied, and whoever has the uh, earliest end time, right, is going to get evicted first, and when that person or when that cow gets evicted, the next cow goes in, right, and then you rinse and repeat that process. Um, Now, to figure out the smallest cow, if k is small, then it's not that bad. But if k is a relatively large number, then every single time we're inserting a cow, we have to go through each of the k cows and determine like what is the earliest end time, right? And that's clunky. We don't want that. So instead of that, we can use a priority queue that prioritizes uh, the end time of any cow that's currently on the stage. Okay, so if we're to use a priority queue, so k is still equal to 2, all right? So we're going to start out with the q with just the number 4, but it's got more capacity, right? Because k is 2, so we can actually fit the next cow in, which is going to have an end time of 7, okay? So the priority queue is going to be like, oh, cow 4, the cow with an end time of 4 is going to finish first, okay? So I'm going to evict that cow, right? And put this next cow in with a duration of 8. So um, one thing you have to note is that you have to calculate the end time. So you do need an additional variable to keep track of, like, at the time when you evict that cow, what is that time? Uh, well, in that case, that's 4, right? So, so you put this next cow in with a duration of 8, and it's going to end at time equal to 12, right? And in fact, since it's a priority queue, it self-sorts, right? So that 12 is here, okay? Right, this is simulating cows 2 and 3, okay? And cow 2 is going to get finished first with an end time of 7. So the 7 gets evicted, and then the next cow goes in with a duration of 6. So 7 plus 6, that's 13, right? So the next cow comes in, and it has an end time of 13.
Wait, so that actually works?
Yeah.
You can just keep adding to element 0?
Wait, what?
You can just like keep adding to like the first element until you're done with the entire array?
You can just keep, as you're evicting, you're also adding the next cow into it, right? So you just keep on doing that until you reach the end. So with a
Okay.
priority queue, you don't really need to do that that much. You don't really need to be that clever. Once you set it up so that it sets up, it stores the cows based on the end time, and then the last cow. So this cow, I believe is cow 3 with an end time of 12. That's going to finish before this cow, obviously. So we evict that and put the last cow in, which has a duration of 4. So that's gonna be that cow is gonna have a duration of an end time of 16. Okay. Yep. And then you simulate removing the cows from the priority queue and find the largest end time, right? So in this case, that's 16. Questions? All right. So next one. Let's call it HPS. Yep, so go ahead and read this. All right, are we good? Okay.
So
Got it.
could you like use prefix summarize?
Hmm. Interesting. What would you do
Like,
with
see
it?
how many matches each one would win.
Can you be more specific about this prefix sum array? What is its dimension and what does it store?
Like, it'll be the dimension will be the number of games, and for each letter there'll be a separate array saying how many games it'll win if you just play it up to a certain point.
Yeah, so there's 3 letters, so that's like 3 arrays. In fact, we can make a 2D array out of it. Either way is fine. Yeah, so if I get this right, so we can do like a prefix sum here where prefix of I and j denotes the number of games Bessie wins when she after I rounds when she starts with hand J, right? So there's 3 different possible hands, hoof, paper, and scissors, right? And there's N rounds. So yeah, keep in mind that she's only allowed to change hand once, right? So we can have like a prefix sum thing here where it counts how many times she wins after I rounds when she starts with that particular hand. We can very similarly have, I guess, prefix. The opposite of that is a postfix, right? That goes the other way, and we can say postfix of I and j denotes the number of wins Betsy have from round I all the way to round N when she ends with hand J. She can start with one hand, she can end with one hand. Like at a certain point, like she can change hand. We don't know where that certain point is, but we can loop through that to find out. And once
Chi-Bomb.
we have these 2 arrays, yeah.
My VM is like doing something weird. Whenever I move my mouse, like the screen moves in the opposite direction.
Oh, I don't know why it's doing that. Can you try refreshing that page?
Okay.
Yeah. Is it?
It's still doing it.
All right. Do you mind if I restart your VM? You will lose your work. You're gonna have to reopen the windows. So save everything first.
Okay.
All right. So I'm gonna quickly restart link.
Yeah, you can restart it.
All right. And okay, there we go. Yep. So once we have these 2 arrays, then we just have to continue on to the next page for I in 1 to n, right? We just have to determine at which round do we switch in, right? So we want to find the max of max over I, right? Where it's prefix of I, j. Actually, so this is going to be a bit unwieldy, but yeah. So if you switch at after round I, then right, you want to do the postfix from I plus 1 all the way to the end of the array, right? So that's your solution. All right.
So is the thing that tips you off that you want to try prefix sum the indication that there's like a specific game that she can switch so that it kind of know that you should use prefix sum and postfix sum?
Part of why it tipped me off was it was similar. It's actually really similar. I don't know if you remember that marathon problem as part of homework a couple weeks ago, but the structure of it is very similar. Like you're allowed to have one checkpoint skipped, and you don't know which checkpoint that is, so you have to loop through it. And here, in this case, you're only allowed to switch one, so you don't know where that is. So that structure is similar. Um, and the other thing that tipped me off that we can use a prefix sum is I need to know, like, at a certain point, like how many rounds Bessie has run, right? And then the next round, uh, right, that number isn't going to be changing that much, right? It's either she wins that round or not. So it's going to be either the previous +1 or the previous +0, right? So in that sense, that also tips me off that we can do a prefix sum. All right, so it's 4:35. We can squeeze in at least one more, if not two. Okay, so this one is called cow code. This one's tricky. We have not looked at problems like this before. We good? All right. So n here is a huge number. It's not like the usual 10 to the power of 9. That's usually the limit. Like 10 to the power of 9 is 1 billion, and integers can only store int. The data type int can only store up to 2 billion-ish. So here it does tell us to use a long instead. Okay. So looking at this problem, there's something recursive about this string, right? Where you start with the pattern, right? So let's say like COW, right? And then if you're to expand that sequence, right, it becomes so if you're trying to figure out the next set of strings, right, you can essentially copy the old string and you're almost there. You just need to do like a little rotation, right? So the W goes here and the rest gets pushed. Okay, and if you're trying to figure out the character at a certain position, what you can do is you can do this over and over again. Right, so if I were to expand that string again, it would look something like this, right? Where like this is the new half that I put into it. Okay, now I don't actually get to create this string. Why is that? It's because n can be so large, and it's clearly impossible for us to create a string of length n. right? If we could do that, that wouldn't be that hard. It would be a fairly easy problem, but we couldn't because n is so large. So we need to figure out what the letter is at position n without the benefit of constructing this string. So how do we do that? One thing to notice is that recursive thing that we just did. So if we're to expand this string, right, so it starts a cow, and then if we want to get like the next sequences of letters, right, you basically make a copy of that, right, and then you do a rotation, right. So it looks like this. Notice that operation that you just did, it increased the size of a string by a factor of 2. Does that make sense? So we went from a string with length 3 to a string with length 6, right? And if we were to do that, if we were to iterate again to get like the next sequence of strings, like you would effectively be doubling your string length as well, right? So you're doubling again to eventually be able to figure out the letter at position n. So we can't do the actual doubling, but maybe we can look at this and see if there is a pattern where we can map, like for a given position. Right. So if I refuse to do that in this next iteration, okay, let's say like I would run out of space. I would run out of memory if I try doing that. From looking at just where I want the thing to be. So let's say I want the letter at this place. How would I find that? Well, what I can do is I can look at I can split the string into essentially 2 halves, right? And if the letter that I'm requesting is in the upper half of the string and not the lower half, then I can do a transformation to get what the actual letter is in the lower half, right? So I'd be looking at correspondingly like the string that the letter. So looks like I'm trying to get like the 4th letter. Is that right? Yeah, I'm trying to get like the 4th letter in this like upper half of this string. So the 4th letter here would be that, but then I need to shift it once, right? Wait, hold on. Is this Korean? Why are the things not matching? Oh, the font size is different. Hold on. All right, there we go. So I'll be looking at like this letter, but I'm off by 1, right? Since I did that cycling, so I would be like shifting to the left by 1 instead of shifting to the right by 1, right? To get what I want. So this would be a W, right? Does that logic make sense?
So are you saying like you chop off the first letter, so that's why it shifts over 1?
Right. Yeah. So what you want to do is iterate on a process where, given that s of I is the string expanded by I iterations. So at every iteration, we expand the string length by a factor of 2, right? So given we have s of I, so let's suppose n is between length of s of I and 2 times length of s of I. So the notation here is a little bit confusing, but why am I saying this? Because if n is strictly below length of s of I, then we just need to index into string s of I, right, to figure out what the nth letter is. But if n is over length of s, but within a factor of 2 in it, right? Then we can do that process where we can try to figure out. Then we can figure out letter at position n by looking at an index within s of I, even though n is technically out of bounds of string s of I. Keep in mind that we can do this without knowing what s of I is. So once we figure out which index to look at within s of I, then you can iterate on this process to see which index to look at within s of I minus 1. And then iterate on this process to see which index to look at within s of I minus 2 and so forth until s of random number k such that s of k equals the original string. Questions? All right, so to be honest, I don't really know what to assign for homework. We've talked about these problems. We've gone through 1, 2, 3, 4, 5 of them. How about this? I'm going to ask you guys to write up the solution for 2 of these. Okay, so pick any 2 of them and actually implement it in code for your homework.
You send us the list in the email.
Yeah,
Like,
yeah.
okay.
Sure. All right. So that's it for class, and I'll see you all tomorrow. Bye.
All right.